Tonight's class is about the world of inductors. We're going to dip our toes in duty cycle also, talk about how to identify a good inductor, what the effects of magnetism are on inductors.
Just remind everybody of what our mode of operation is going to be in here tonight. We're going to assume for the purpose of tonight's class that everybody here at least has a solid understanding of the basics of Ohm's law, the behavior of voltage in a circuit, the behavior of current flow in a circuit at a basic level. However, that doesn't mean don't ask a question about it, because if you have a question about it, I'd much rather us address it as a group, get things squared away, get that tied down and move forward, than to have somebody, you know, sit here and get lost or go, what just happened? So please feel free to ask questions. If you've been on one of these webinars with Rich and I, you know that we like things to be as interactive as we can be in this environment. And so it's your class, ladies and gentlemen, it is your class. Ask questions, raise your hand in chat in response to yeses or nos, leave them up until we ask you to put them down, so we can kind of get a total look at how many people responded. Feel free to use the chat, set it to panelists and all attendees, if you please. Reason being is, if we respond to something in chat and you didn't share it with the rest of the group, it's really hard to pick up on where did that question come from. So please do that. What we're going to do tonight is continue on. So we talked a lot about Ohm's law, and we talked about rules and how Rich hates rules and I'm a rule monster. No, we have different ways of teaching, and most of us hate math, and we can get into this stuff at a technical level to the point where we go, how's that going to help me fix a car? And I've asked those questions in classes myself. So if I find myself going, how does this help me? Then I tend to put it off to the side as like a cool topic, but not necessarily something we've got to make sure everybody pounds in and memorizes. If you want to go there on your own, fine, have at it. But what we definitely want to do is we want to take our knowledge and understanding of a system, and we want to use a logical and methodical approach to diagnostics. And so that's what we're going to try and do. We're going to talk about a system, and then we're going to go, how can we use that to understand the system, and how can we use that to diagnose the system? I don't know how many instances of files and simulations and stuff open on my computer to share with you guys tonight. And so if I'm looking to the side, I'm looking over at a different screen, and I'm looking for one of the open resources that I have that I can drag over onto the screen to share with you guys so that you can see what I'm talking about. And sometimes I may be setting up the next simulation off to the side. So Rich, jump in if I look like I'm off to the side there for sure.
Absolutely.
Randy's going to, he says Rich and I are co-hosts, but Randy's going to participate in this tonight as well. He may not have known it, but he said we were having fun tonight. So that's what's going to happen. So with that being said, when we talk about logic, we're talking about being methodical. We're talking about having a plan. And what goes into the plan is our understanding and our knowledge. How well do we understand what's happening? From that, we want to do one thing. We don't want to do 3 or 4 things. We definitely don't want to do 6 things. We do one thing. We understand what that means to us. We look at it. So just because we did a test and it says move to step 3, why am I moving to step 3? Why is what I just tested good? And that's the way we want to approach everything we're doing, especially with electrical work, because it's so logical and rule driven. And then we're going to act on what we found. And for those who have heard this talk before, that plan, do, study, and act is a repetitive cycle to keep us from getting lost. I was having a conversation with a friend of mine, and he was saying we should probably do a course just on this with maybe 10 or 12 examples of how we apply it. But we're going to try and implement this throughout the class tonight as we move through some of the conversation. So one of the things that came up in the previous electrical classes was talking about duty cycle or pulse width, and what impact does that have on an electrical system. And I started looking at that, and I'm like, you know, there's a ton of ways to come at that. And so when we think about it, it's like, well, what are we trying to accomplish? What are we trying to do? What's the circuit, and what is the condition we're trying to create with that circuit so that we can appropriately control the system on the car? And then one of the other things that I think we run into a lot on vehicles is sometimes description and operation can be pretty confusing. And so real quickly, I'm going to give you an example of a control system that's pretty common. It's warm weather in most of the areas that people are tuned in. And so I'm going to give you an example of a blower motor control system. And if you guys have been on a previous class, we did this one on Monday night. So just bear with us, but I'm going to go through it quickly because I want to put some time into some other systems. If we look at this blower control system, and folks, we don't have a huge audience here tonight, but we have the ability to turn microphones on. I'm actually gonna demonstrate that with a participant that now has the ability to talk, and they can unmute their mic and jump in and say hello to the group. Hey, Anthony.
Now you're expecting me to actually know how to hit the mic button. Hi, guys.
So go ahead and mute yourself back. I'm
Aww.
not going to put you on the spot first thing. I'm going to save that for later. And look, this is one of those things where we've all been in classes, and sometimes you're sitting there and you don't really want to engage. You don't know everybody, and we all are like, oh, what if I answer it wrong? Who cares? Right, Rich? Who cares?
Absolutely.
Who cares?
I'm wrong all the time.
Me too. Me three. This is the perfect place to be wrong. We don't have a customer's car that has to be out. There will be no money involved. There will be no parts damaged in this unless they're here in my computer room. So we don't have to worry about that. And what better place? We learn more from what we mess up than we do from what we get right. And if you guys haven't used this concept in your day-to-day work, when you finally get a car fixed, learn backwards from it. Go back through what you learned. Where did I do a test that maybe I didn't need to? Where was my plan off that made me do something that didn't actually progress me forward in my process? And that's that backwards learning that we should always employ. It's like an after action report in the military or the fire department or whatever you want to use as an example. So here's the thing. I've got a wiring diagram up here. Who would like to come on here looking at this wiring diagram, if you can see it clearly, and give me an idea of how this circuit works? Is it magic? Is it some form of I don't know what to say, Rich, or is it very logical in how it works? Who would like to maybe come on? Raise your hand if you want to turn the mic on and basically just talk me through pointing the mouse or pointing the laser pointer. I can turn a laser pointer on here. So, and I'll follow your flow. Anybody want to play that game tonight?
Want to tell us how the blower motor works?
That's it. We're looking for the blower motor. How does this blower motor work on this vehicle? A little too small. Sorry, Bob. I don't know what kind of a screen you're on. If you're on a PC.
Laptop?
Laptop. Interesting.
I see it okay.
It depends on the size of the laptop. So, if it's a 12-inch laptop, I can see where eyes could be tough. I've got it up on a 32-inch screen, so I see it great. All right, let's do this. Rich, you do it. You explain using numbers and descriptions. Explain to me how you think this blower motor works.
Ah, jeez. Now you're putting me on the spot. Okay,
Absolutely. And you know what? This is unscripted, folks. This is real world. So we get a car in, we've got a component that's not working. This car just came into Rich's Bay, and it says the ticket says, blower inoperative, or blower runs all the time, or blower doesn't run at all. And I don't see any resistors on here, Rich, so have at it.
All right. So what I can tell from this wiring diagram, power at the top is hot at all times on all of those fuses. So the switch, power being fed into pin 30 on the relay, the blower relay itself is hot at all times. And fuse F5, 7.5 amp fuse, is feeding power to pin 86 on the relay. So in order for that relay to work, pin 85 needs to be provided a ground. So I can pretty much safely assume that blower request on the HVAC module provides a ground that energizes the blower motor relay, which would provide power to the blower motor and the blower motor speed controller. From there, what's happening inside of the blower motor speed controller is magic. From what I can see on the wiring diagram, we have a VBC set point, and that wire going to the HVAC module, and that is labeled VBC output. So I am assuming that the HVAC module provides some type of a signal to the front blower motor speed controller, and based on that signal, the blower motor speed controller is providing a pulse width modulated ground to the blower motor, since it's getting constant power from the relay.
So there it is. Some type of pulse width modulated ground. So what does that mean? In the older systems, Rich, we would put multiple resistors in here, right?
Mm-hmm. Yep.
So we would mechanically dial on one side or the other to force the power through a resistor. And what happens when we put a resistor in line with the motor?
We have two loads in series, and the voltage is dropped across both loads, so the blower motor will turn slower.
Okay. So if we're not doing resistors and we're running, I'm seeing the HVAC module ground circuits are not identified on this diagram.
We might have cut it off in our cropping for the HVAC module itself, I guess.
Actually, we didn't cut it off in its cropping, and this is a great, the great thing about reading diagrams that a lot of guys forget. So I'm going to take a point to point that out since it was mentioned in chat. Anytime you are looking at a wiring diagram, the standard convention works like this. This blower motor has a solid blue outline. That is a complete view of the component. The blower motor speed controller has a solid blue outline. That is a complete view of the component. Since this HVAC module has a dashed outline inside of that blue, that means it is an incomplete component view. And there could be other wires, connectors, and things that attach to that module that are not shown in this drawing. And that is something to always keep in mind. The same way that this general junction box or central junction box, this is only a partial view of that junction box and does not include the whole view. So the fact that that particular ground isn't shown is not actually important to the operation of this blower circuit, if that helps. So Matt, if you've never heard that before, that's one of those, Rich, it's one of those rules about making an appropriate wiring diagram. That if you remember that, anytime you see those dashed lines, it's like, I don't have a whole picture here. So if you're trying to diagnose something and you want the whole picture, look, what? There's more to the story.
Dotted line means there's more to the story.
There's more to the story. That's a great way of putting that, Rich. So getting back to this pulse width control, if I have power to this motor and I ground it, it's going to run full speed. If I don't have any resistors, I'm going to have to do something different. And so with the motor, when we take and ground it and turn the ground off and ground it and turn the ground off, if we did that slowly, we would hear, and excuse the sound effects, folks, but you'd hear vroom, 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 right? That's cool. Awesome. But we don't want that inside the car. So we're going to turn it on and off at a frequency that's fast enough to establish a blower motor speed. And what ends up happening is if we turn that ground on and off fast enough, we will get a steady speed. What we have to figure out, though, is how long is it grounded versus how long is it ungrounded. And that's where the phrase duty cycle comes from. So the longer that it is grounded, the faster the motor will run. So to give an example, if I were to duty cycle it at 50%, which means it's on half the time and off half the time, and do it quick enough, the motor will effectively be supplied half of supply voltage, and the duty cycle control will act like a dynamic resistor to limit the speed. Is that cool? So if I duty cycle it on 100% of the time, that means it's always grounded. So if it's always grounded, the motor will get full system voltage and will run at full speed, and anywhere in between. That's the way, that's the basic way that that logic works. Any questions so far? Duty cycle and pulse width are two different animals, and I often see techs assume that they're the same thing. So pulse width refers to time. Would you agree with that? Okay, so we got Brian's agreement on that. So within the time, we can still establish a duty cycle. Okay, so think about it like this, Brian. Let's have a via chat conversation, or I will turn your mic on if you want, whatever you want to do. As a matter of fact, we have a vote to unmute your mic, Brian. Are you good with that? Brian, please respond. Please respond.
Oh, he's got to get his headset. We put him on the spot.
I have to get my headset. Cool. Well, I'm going to go ahead and click on allow to talk, and when you've got your headset, you can come on here. But I'm gonna throw something out here. When we look at the command to a purge solenoid, right? We can see that purge solenoid would be commanded at some duty cycle, right? So if we look at what happens, we turn that purge solenoid on. Hey, Rich.
Yes.
Do you have an instance of Pico open?
Yes, I do.
Go into let me see if I can do this. If I go into automotive and I go into actuators and I pick up an idle speed control, electromagnetic, I get something that looks like this, right? So when we turn on that solenoid, when we turn the power on, the current flows. So this is like current here, right? We get the current to ramp up, and then we turn it off, and ramp up and turn it off, ramp up and turn it off. And that solenoid is pulsed open and closed. So in this case, this is a pretty slow type of a signal. Okay. And what we're really controlling here is both the mechanical valve opening of that purge solenoid, but what we're controlling is the amount of purge vapor flow. Everybody good with that? We're controlling the purge vapor flow. And so if we turn on for a 20% duty cycle, then the amount of on time is relatively short. And we will get that valve to open, but only briefly, and so only a small amount of vapors will flow. If we increase that duty cycle, then the purge valve will spend more time open than it was before, and we will get more purge flow. That same concept can be applied to controlling an electrical device. So if we turn a light bulb on and off really fast, we can control the effective amount of voltage that goes to it. Brian, are you there? I thought I heard noise.
I'm here. Can you hear me?
Yep.
Yeah, absolutely. Audio's good. Audio's good.
All right.
So did you have any headache with the way I just described that?
I was not listening. I had to.
You had to go get your.
My
you had to
headset.
go.
It was on my PlayStation.
Okay. So let me. It was on your PlayStation. Great. That's a good place for it to be. How about if we have this conversation? What we're doing here, we're just getting our terminology right. So if I look at this command to the injector where we ground the injector, we hold it for a period of time, and we release it, and we can see that it flows current over that period of time. And we'll get into this whole inductive kick thing and everything here later. But if we're looking at this, would you be okay with me calling this our pulse width?
Yes, absolutely. That pulse width is exactly what it sounds like. It's the width of the pulse, the actual
Okay.
on time.
Now, if I put enough of these on the screen and I have a fixed RPM, okay, so I'm holding the engine steady at 800 RPM, and I put enough time on the screen, could I move this and incorporate multiple injector functions that are all at the same pulse width and get a duty cycle reading off of my scope?
I'm not sure how to answer that.
Ooh,
That's interesting.
I am the vortex. Yes. Okay. So that's an inside joke. Brian comes up with great questions, and we love to challenge each other with theoretical questions. But the answer is you can get your picoscope to calculate a duty cycle off of a pulse width signal if you have enough time on the screen.
Yeah. Okay. I understand that. But I usually relate duty cycle when it comes towards signals that are on and off very quickly, and you're comparing the off time to the on time.
Okay, and yet when we look at the PID for our evap purge solenoid,
yes,
it's described as duty cycle.
Yeah.
And it's not relatively fast compared to like a lighting circuit control. Would you agree with that?
Yeah, absolutely.
Okay, Jim, let me
Yeah.
add a perspective to this, if you would.
Oh, here we go. We're going to triangulate on the topic. Let's go.
And you guys chime in, tell me if I'm crazy about this, not in general.
Oh, okay. All right. Thanks.
So, I consider pulse width to be kind of a one-shot deal. The measurement that I'm trying to take is one event, even though it happens multiple times like an injector. The measurement that I'm taking is one event. When I consider duty cycle is typically, not always, because there's never an always, but typically a fixed frequency. So a fixed number of cycles per second, and my measurement in that is the amount of on time compared to the amount of off time. That's expressed in percent, and that's where we get duty cycle.
Yeah, that's kind of what I was getting at.
And I agree with you guys. And where I'm going though is that electrically we have dynamic things happening. And so the way we look at it, it doesn't really matter as long as we understand what we're trying to measure. And so I can look at a pattern of pulse width and okay, so I can measure the pulse width of that vapor valve, right? But it's typically done at a frequency, and so I can still give you an on to off time representation if I look at enough time on the screen.
Yeah, the frequency is usually fixed, and the
so the injector is not a fixed frequency because it's going to vary with engine RPM.
Yes.
Right? But another device that's controlled the same way electrically with a transistor that toggles it to ground and releases it could be done at a fixed frequency. And so you could still theoretically look at duty cycle, even though we're really only interested in the pulse width control of that specific device.
So,
is that fair?
So if I'm understanding your statement correctly, with an injector, I'm concerned about how long it's on. I don't care about how long it's off.
Yeah.
If I'm dealing with something that is truly a duty cycle command or signal for that matter, like your purge valve you're speaking of, I'm concerned about how long it's on and how long it's off, because the percentage of each is going to determine the amount of vapor it flows.
And I don't have a problem with it. And this is where I think, you know, good techs looking at, remember, this is a class on understanding how electricity works. Okay. And so when we're trying to understand how a device is controlled, trying to separate them out too far can get people lost. And we're going to get to the reason why as this class goes. So I'm going to say, okay, we've got some slightly different perspectives, but we have a base agreement. So what did you have any problems with what I'm talking about with how this blower motor is controlled with the on and the off time at the frequency that this device produces, controlling the amount of voltage that's available to the fan, Brian?
No, not at all. The duty cycle will change depending on the input coming in. That's
so now we have to figure out, okay, so where is the magic in that? And how does the device actually work? And so here is another diagram. Does this look pretty similar to the last one we gave you?
Mm-hmm.
Yep.
This is actually off of a 2010 Flex, this particular diagram. So we have blower motor relay control. And again, here's those dashed boxes in incomplete views, incomplete view, but these are complete views. So this blower motor speed control, this is a complete view. And I've got a picture of this one coming up. So we have the ability to control the relay. We have power flowing to the blower motor and the speed control. And then we have, here it's called front blower PWM and PWM. And then we have here you can see in this one, Brian, we've got ground for the HVAC module at the same point as the ground for the blower motor speed control. Everybody good here?
Yep.
Yep.
All right. So the question becomes, one of the things that I like to do when I'm diagnosing a system is, if I've had the ability to check for codes or there are codes, I like to look at what kind of codes the system could set. And so this particular Ford can set front blower control codes with symptom classifiers on the back, and it can also code for the front blower relay. And so short to ground, short to positive, or an open circuit for the front relay, or the blower motor control, we can identify either a short to battery positive or a short to ground or open. And that one right there is a key to how this system works. So if we look at what actually happens with this, Brian, what would you call this signal?
Duty cycle.
Okay. That's the pin that Ford identifies as the pulse width modulation,
Mhm.
PWM, to the front blower relay, or the front blower controller, the speed control. Okay. So how would you describe the on time versus off time here?
It looks like it's on approximately 20% and off 80%.
Okay, I actually have the answer right there for you on the bottom of the screen. If you can see,
30,
if you
okay.
can read it. Yeah, so it's about 30. It's hard to eyeball. I'm not going to pick at you for that.
Yeah.
So we're on about 30% of the time, and we're off most of the time.
Mhm.
And if you look at this current line here, that current is relatively low. And then as we continue, what's happened with the on time?
It's about half.
Okay, so it's about a 50% duty cycle. The
Mhm.
current has gone up. Okay. And if we continue, now we're at 75% duty cycle, roughly. And now look what's happened to the current.
Yep.
Is that starting to actually look like a motor current?
Absolutely.
Now we're starting to actually see those commutator brush bars. Okay.
Yeah, it's still duty cycled, but not, it's duty cycled at such a high rate that it's almost completely on.
Okay. But remember, we're providing a ground to the motor to make it run.
Yep.
So what we're providing as a signal to the speed control is a 5-volt signal here. And that 5-volt signal is being interpreted as how much ground is provided, or how much resistance is put in the ground by the pulse width in the blower control motor. Is that a fair way to put that?
Yep.
Okay. So then we're going to go one more here. How would you describe that duty cycle?
That is 100%.
There ain't none,
Yeah.
as we say where I grew up. There ain't none. So there we have pretty much a full 5-volt signal to the speed control, and we're seeing a definite repetitive set of commutator events with the current flow.
What is the voltmeter on ground?
What did I have the voltmeter on? This picture was from
Originally, the voltmeter was reading the duty cycle in the previous screens,
Okay.
wasn't it? Or was it just reading average voltage? I might be wrong on that one. Oh, it's just on voltage.
Yeah.
Oh, you know what?
That was
I
reading average voltage at the ground side of the motor itself.
I'd have to go back through my notes. There was a reason I was leaving the voltmeter out of the conversation. I can't remember. No, as a matter of fact, the voltmeter has an amp clamp hooked to it. And if you did the math on that, you're seeing I'm showing about 16 amps of current on the Pico. And I'm
Okay.
also showing something similar on the voltmeter. If you did the math from millivolts to volts, that's what's going on.
Gotcha. All right, that makes sense now.
So don't worry
Hey.
about that.
Thanks for clarifying that, Jim.
No problem. It's just, it wasn't part of my thought process in the description tonight. So then here's the question that I have for everybody. We're going to go back to this wiring diagram. We're back to this wiring diagram. So what we were looking at with the scope was actually this front blower pulse width modulated input to the blower speed control. If we go to description and operation, it will say that the HVAC module provides a signal to the blower speed control. So my question is, if this blower motor didn't run at all, could it be a problem with this wire?
Sure. That's a missing message. So yes.
Why do you say that?
If the message isn't there, the controller doesn't know what to do.
Okay, actually, I'm going to show you something. Here's the blower motor speed control. I have supplied it power and ground. There is no HVAC module in play here. Okay. If you look at my voltmeter, it's connected to
Pin number 3.
pin number 3. Okay. And with this speed control powered up, it's providing 4.73 volts.
Okay, so the controller is what's pulling that circuit to ground, not the HVAC module is what's pulling that signal to ground.
And so Brian, you know why I'm doing this and why I'm saying that having that little piece of information is really important, is because if this thing is putting out that voltage and it's looking for that HVAC module to toggle it, to twang the string, if you will, to pull it to ground.
Mm-hmm.
Okay. So it knows what to do with the blower motor. Then if that wire was cut or open, this system would run the fan wide open every time the front blower motor relay was powered up, because click and 100% duty cycle, which means no grounding signal from the HVAC module, that fan runs full speed all the time. So if you ever have one of these Ford fans like this that fails and it's running full speed all the time, it's not a problem here, it's not a problem here, and it's probably not a problem here unless it's not pulling it to ground. But if you unplug this wire looking for that control signal from here to there, and you didn't have it, it's because you just took the voltage away from the blower motor supplying it. So knowing who sets the control or the communication line is important. And when we looked at the code set, okay, the front blower circuit, the blower control circuit, the conditions would be a short to B plus or a short to ground or open. And that condition 14, if you had that code and the fan was running at all times, the first thing I would check would be that wire between the blower control module and the HVAC circuit. Does that make sense? Guys in chat, what Paul, not based on what you showed us. All right, explain that.
I think what Paul caught was that if you go to the full speed signal, he was able to pick up that not providing a ground would cause the motor to run at full speed.
Paul, is that where you were going?
Yeah, without the HVAC module pulling it to ground, it's going to assume
It's
that
going to run full speed, yeah.
full speed. Yes.
Correct. Okay. Oh, so that was earlier in the I must have missed when that conversation actually took place. All right. So let's look at something that is similar but different. Let's look at another circuit that looks almost identical and talk about how it works real quick. Here is a Toyota blower motor. This is most of their new ones. And what you're seeing here is the blower motor and the speed controller integrated. So if you look at this, that says blower motor, and this is a full solid line. So that's a complete view. You have a blower motor with 3 wires, hot at all times, ground, and a speed input or a signal on the light green wire. And this obviously can't work the same way because there is no relay to cut this thing off. That blower motor always has power and ground. Toyota provides no codes for this system. GM blower motors are almost identical, and they provide codes. I'll let you decide which one makes more sense. So, if we have power and we have ground and we do not have a signal here, this motor's not going to run. So here's an example. Here's a picoscope file. As a matter of fact, I have these. Let's see. I have a whole bunch of where'd you go? There it is. Here's the actual picoscope file.
It's impressive.
Huh?
It's impressive.
Why is it impressive?
There's a lot going on.
There's a lot going on. But if you look at this, channel A is fused power. And so you can see that's 12.5 volts there roughly. Mm-hmm. Channel B is ground. And so we're showing a good ground. Channel C is the speed control. And if you look at that,
it looks like amperage.
No, it's just voltage.
Oh, I'm sorry. I'm on D. Go ahead.
Yeah. And D is current. Yeah. So the brown trace is current. You can see that's pretty much 0. So this is actually key on, engine off, right? And I'm hooked up to this setup, and this is proving exactly what we just showed in the wiring diagram. We've got hot at all times. We have voltage being supplied to what Toyota would call the HVAC amplifier, right? The AC amplifier. We have a solid ground, but we have no current flow. And so this one works completely differently. So if we take a look at what happens with this, we get to, this is a picture of the picoscope file, and I have this one here as well. But if you look at this, here we are, key on, engine on with the blower commanded off. And so the HVAC system is powered up, and there is a frequency of control and a duty cycle that could be measured if I zoomed in on this, but there is no current flow. And what I have done is gone from 0 speed up to speed 31 according to the scan tool, and then back down. And so unlike the Ford system, this one is always running a piece of control, but it works very differently. So right here with no current flow, you can see the section I'm zoomed in on. With no current flow, the duty cycle is showing 85% because it's left high most of the time and pulled down just briefly. And the logic in that blower motor is saying, okay, they don't want the blower motor to run. And then as we ramp up to full speed, if you look at the window on the picoscope here, now I'm at full speed. The fan is drawing 11 amps. And this is a brushless motor, by the way, so the current flow is pretty low on this thing. But the duty cycle is only making it to 40%. So with the fan commanded off, it's at 80-some%. With the fan commanded to full speed, it's at 40%. Anything other than that is not a valid signal, so it won't run. Okay, so it's commanded off, it's commanded up to full speed, but it never gets to a 100 or a 0% duty cycle when the HVAC module's on. Is that a good piece of information to keep in mind? And I say, yes, it is.
That rules out the ability to have a short circuit to ground or an open circuit, you know, because that's not a plausible type of scenario that would affect the blower motor.
Correct. Absolutely, absolutely correct.
It wouldn't be stuck on high with it, you know, open.
And I will add that while you were talking about Toyota, Jim, I opened up a 18 Escalade, a GM, and the signal is nearly identical. So
Yeah.
the GM and the Toyota systems are almost identical.
And again, the blower motor module sets that 5 volts. And so the HVAC module only toggles it to ground.
So
knowing that kind of stuff is absolute key. All right.
I was going to say you have to be careful because Toyota and GM label that green center wire as speed input. So guys want to unplug the blower motor and scope the speed input signal, but when you unplug the blower motor, you just lost your 5 volts and you're not going to see a signal.
Correct. Got to back probe that one. All right. So then we start having to think about more of what's going on. And so this is a huge topic, and we have to realize what was my quote of the year from Monday night? Electricity and control of systems is a dynamic environment. Randy Briggs, 2020. He's probably been saying it for a lot of years, but there it is. And so we can get into the laws and the rules, and we can talk about Kirchhoff, and we can talk about Lentz, and then we can talk about Faraday, and we can talk about all kinds of specific laws and rules. But for our purposes, what we need to understand is that it is a definite dynamic environment. And so these are some slides that Randy actually put together, and they have some real valid application, but they're kind of blending the topics all together, and there's nothing wrong with that. And we're basically pointing out here that if you have electricity flowing, there's a magnetic field that's being created. if you have a magnetic field moving around a piece of wire, there is induction taking place. We are creating current in the wire. It may be very small or it may be rather intense. It depends on the levels. And so if we're going to use a device to turn electricity into mechanical work, this is one of the ways that it's going to happen. So if we're going to make an injector move, we're going to, and open a pintle, we're going to flow current through a coil of wire, which is going to create a magnetic field, and that magnetic field is going to pull a pintle open. And depending on the pulse width or the on time, and depending on the strength of that magnetic field, is going to determine how long that pintle is actually open. Pop quiz. Is the pintle open for the same amount of time as we see in pulse width? Yes or no? Put it up in chat. Yes or no? No, no, no. I'm seeing some no's. Excellent. Excellent. And so what does that mean? It means that when we flow current into a coil of wire and we create that magnetic field, as that magnetic field is building, it is fighting against the flow of current. So there is a ramp. Let me see if I can bring that. Let me see if I can bring this back. So here's a fuel injector. We completed the circuit by grounding this injector, and current started to flow. And because that magnetic field is building, it's fighting against the current flow. So that's why we don't see the current jump straight up and flow. What we see is the current gradually ramps up. And so in the process of this build, this magnetic field is getting stronger and stronger and stronger. At some point, the magnetic field will overcome the spring and the fuel pressure that's holding that injector pintle down. And so that pintle will move from a closed position to an open position. Well, as soon as that piece of metal moves in most injectors, and Randy pointed this out on Monday night, in most of the older injectors, the bigger injectors, that piece of metal was significant enough to where when it moves, it causes a disturbance in the magnetic force. And that disturbance in the magnetic force will cause this little bobble in the current flow. And so we've learned to read this as a pintle hump. And it's hard to see on some of the new injectors, but you can see it if you would current ramp a air conditioning clutch coil. You can see it if you would current ramp a door lock actuator. When that door lock actuator pulls and moves that locking mechanism, when it moves, you'll see some type of a disturbance in the device. And so the actual on time of that injector is actually from here to here. And so what does that mean? It means that anything that affects this circuit will affect the mechanical operation. If the windings in the coil have a problem in them, either excessive resistance or not enough resistance, the strength of that magnetic field is impacted. And that basically boils down to the things we need to keep in mind. What is the characteristic of the inductor or the solenoid that we're dealing with? How many turns of wire are there? What is the size of the conductor? So size and quantity of conductor. And the core type, everybody likes to talk about this, but I kind of push back on it. The purpose of the core type chosen is to concentrate and strengthen the magnetic field. And that's another key in talking about magnetism and electricity and how much we're actually going to induce. So if I'm trying to build a more compact coil, if I put an appropriate core in it that attracts the magnetic lines of flux that are built by flowing electricity through it, I'm going to create a magnetic field where the flux lines are tighter to the core. And that means I don't need as big a unit to get the job done that I'm trying to do. If we look at wheel speed sensors, the traditional type of wheel speed sensor, they put a core, a magnetic core inside of the windings. And so there is a magnetic field that is basically sitting there. And that magnetic field has an intensity to it. And with a case of a wheel speed sensor, we actually will take a piece of metal and pass it by that wheel speed sensor. And by doing that, we cause the magnetic lines to bend and try and reach out and grab the little tab and then release it, and the next one comes by, and so on, so on, so on. And that effectively creates that positive and negative pulse or that sine wave that we can measure looking at the car. And of course, we have others that generate square waves and so forth. But the rules, what impacts how it works. So if we look at our slide in the background, number of turns. If I have the same size wire and only 2 turns, and I move the magnet past it, I get a certain amount of voltage. If I go down here where I have more turns of the same size wire, and I move at approximately the same speed, I get more voltage. So the 3 things that we're really focused on are size and quantity of the conductor, strength of the magnetic field. Notice out here, because the field lines get weaker as I get farther away, if I'm out here, I'm not really doing much with voltage. You can see it maybe jump a little bit once in a while. But as I get closer, the magnetic field gets stronger. And so with the same relative speed, I can produce more voltage. So size and quantity, strength of the magnetic field, and speed of interaction are the rules that we need to keep in the back of our head. Randy, did I do your slides justice? Are you good with how I went through that?
Yep, that works for me, Jim.
That works for you. Okay, so good. So then the question becomes, what do we do with all this stuff? How do we apply it? And let's see. I've got an example of where we use electromagnetism to control a mechanical device. This is just one example. We're going to do another one here in a minute. Variable valve timing. This component right here out on the end is what? A solenoid? So we have an electrical solenoid, and we have a spool valve, and we have normal timing. We've got the timing moved back, retarded later in the rotation of the engine, and we can advance it. So if you watch, when I go from retarded to normal to advanced, one of the things we have to remember is how this is all working. So if you think about some of the newer systems, if you've done any research on it, a lot of times, not like this system, this spool valve is actually located in the end of the camshaft. And so it's actually mounted in the center of the camshaft, and the phaser is on the front end of it. There's a real close couple here. But but we have an actual actuator that's on the outside. The principle of operation of these things is similar. So what happens is, by changing the duty cycle to the electric solenoid valve in conjunction with this spool valve and a spring, what we are able to do is, if we increase the duty cycle, we increase the strength of the magnet. That magnet will overcome a spring and cause this valve to move one direction or the other. It's going to depend on where the spring is. But the whole point is that the big piece of metal that's being moved by the solenoid, if we turn that magnet to full power, it tries to get the spool valve, the control head of the spool valve, to center itself in that magnetic field. Okay? If we reduce the power on it, it will move less and the spring will win more of the fight. And if we reduce the power more again, the spring wins more of the battle. So we can move this thing to a position where oil could flow into one side of the chamber, or oil can flow into the other side of the chamber, or at an intermediate level, we can hold a position because we don't want to advance or retard the timing. And on some of them, a normal position will cause it to, go all the way home and lock. But think about that. Because I can change the strength of the magnetic field based on time, I can change the strength of that counteracting force against the spring, and I can cause that mechanical movement to go to a position that I physically want. And if you look at a lot of the newer cars, you will see pieces of data like, what is the duty cycle when I know I'm moving the cam in X direction? What is the duty cycle when I know I'm moving the cam in Y direction? And what is the duty cycle when I'm holding the valve timing that I currently want? And the ability to see that data can give you an idea as to how well that particular system is working. Let me go and bring up another one.
Well, while you're finding another one, I just want to tell everybody what you're looking at right now is Moto Visuals, and Jeff put up a link to it in chat. These animations are designed for your customers, so that you can, as you see at the top of the screen, says email. You can email them these animations to better explain whatever repairs they may need or problems they're having with their car. So this is actually a really cool website to check out. Sorry, Jim, go ahead.
No, and to tell you a cool story, in preparation for this class, I was like, hey, Rich, from a standpoint of electricity and magnetism and Faraday's law, an alternator is a really good example of how this all works. And so I brought this up and I showed it to him, and what was your response, Rich?
I wish I had known about this. I was like, oh, that's cool. And it is free to educators, to teachers. I know we have a couple of instructors on.
Okay, so when we think about how electricity and magnetism and everything work together and interact, this is probably one of the best components on the car to tie it all together. And so what we have is an electromagnet in the center of wiring of a specific size and quantity, and there happens to be 3 phases of that wiring because we're trying to produce a smooth power supply to an engine. But this is raw. This is everything stripped away. So here's my question. Everybody type it into chat. What are the 3 important things? Now, believe me, Randy says core material. And when we look at the way this rotor is wound and these big pieces of metal and what that metal is made out of, That is the core structure of that rotor, and it is important because it concentrates the magnetic field in tighter and doesn't let it propagate out here. We're not trying to magnetize a valve cover. We're trying to pass those magnetic lines through this rotor, okay? And so what are the three things? Give it back to me. What are the three things that determine how much voltage I'm going to create in these wires here? And right now it's above and below zero, but what determines how much voltage I get? Pete, that's actually a good point, Pete. He says it's just like the air gap on an ABS wheel speed sensor setting a DTC. When we get too wide of an air gap, we've actually reduced the strength of the magnetic field. So even though the wheel is moving, it's not causing a disturbance in the lines of flux enough to generate a good enough signal. So speed, number of coils, and power of the magnet. There we go. Rotor speed, rotor size, and amount of windings. So the windings around the stator, absolutely. Rotor size, think about it more like the strength of the magnet in that rotor. Okay, so looks like most people got that straight. I'm not going to spend a bunch of time reading it. Rich, that's your job. So here's the deal. As we're driving down the road, can we change the size and quantity of conductors in these three phases? No. No way. We can't do it. Can we rewind this rotor or change core material? Nope. That ain't happening either. You got to be really fast. I know some of you guys can probably flat rate some stuff in a serious way. But what do we have control of? We have control of the voltage applied to the slip rings that power up this electromagnet. And so that voltage regulator, or in the case of some of your Chryslers, the computer, in case of some of your smart devices, it's still the same. We are turning on and off the electrical power supply to this rotor to determine the strength of this magnet. And so the reason we need to change it is if the engine is running fast, this speed of interaction here is very high. If I have this rotor just powered hot and ground, I'm going to have a really strong magnet, and I may actually produce too much voltage, and we'll start popping light bulbs and doing all kinds of crazy stuff.
That sounds suspiciously like a duty cycle control, Jim.
That is exactly what it is. It's at an appropriate frequency to maintain a stable electromagnet, and the car is going to, that voltage regulator is going to monitor what that peak voltage is, or the car will, or whatever device will monitor, and will change the duty cycle to strengthen or weaken the magnet based on the speed that things are spinning. And so sometimes that's done predictively, depending on the control unit. Now we're getting into craziness where we see the engine revving up and we back the alternator off to keep it from overcharging or slugging the system. Is this a good example of how Faraday's law works? I think it's perfect. I think it's exactly what we need to keep in mind. And so if I reset this, and then we talk about what we do to control the voltage. So if you notice in the previous version, just like the magnet, when the magnet went one direction or went the other direction, we would get either a positive or a negative voltage / current flow. So what a rectifier bridge does within the alternator is it controls and gives us only the positive side and cuts off the negative side so that we get the DC output from the alternator. So here we see an example of a good rectifier that's properly controlling the DC current. We see that this system's currently charging at 14 volts. what happens if we get a bad diode? Well, if we get a bad diode and it goes open, you like the way they burn up there? I thought that was pretty fun. It's live. If we lose one of those, now we're only getting 2 of the 3 patterns. And depending on the speed that the car is running, this works very much, even though the peak voltage out of those individual channels may be high enough, because there's a dip and there's a chance for it to drop off, the indicated voltage output from that alternator will be reduced. And we've lost about 1/3 of this one, if you would agree with that. Any questions?
I think we're good.
Pete, you're going to have to explain that comment to me. I don't have time to go into it right now, but it looks pretty fun. All right. So now we get to Diagacar. So for those who don't know, these are the Electude simulators. If you subscribe to our LMS or training or whatever, you have access to a lot of this stuff for online training. There's quite a few different simulation scenarios. Some of them are similar faults, but they make you approach the diagnosis in different ways based on what tools they provide you. So we have here, and I know this work order will be hard to read for a lot of you, so I'm going to read it to you. It says, the check engine light comes on, the vehicle runs poorly, diagnose and repair as needed without the use of a scan tool. So they've taken our scan tool away. I don't know if I like that one at all, but we have it, so we're going to ignore some of that. How about that? I'm logged in under my account, so I'm probably getting really bad test scores for failure to follow directions, but that's okay. We're having a learning environment here. Scope all the things. All right, Paul. Paul, do I need to turn your microphone on? You ready to come in and play on this one? Say yes or no. I'm not trying to put you on the spot, but I'm putting you on the spot. You want to chat? Sure, I like it. Paul, let me find you here. There. If you
Can you hear me?
Absolutely. Absolutely.
Hey, Paul.
Hello.
So Paul, there's no right or wrong way. You may choose some options, but I'm now going to become a servo, which means you have voice control of this servo. Have you seen these simulations before?
Yeah.
You have.
Yeah.
Okay. So for those who don't know, I have an instrument panel. I have the ability to start the car. I can control the noise level there. Can you guys hear that?
Yep.
Okay. I'll shut that off for right now. We have wiring diagrams. We have breakout boxes. We have an oscilloscope. We have a multimeter. No, Brian, I don't have an amp clamp, just in case you were going to ask. When in doubt, pull the Pico out. Oh, Anthony. Anthony, you're doing the next one. Okay. So question for you, Paul. If it says the check engine light comes on, it runs poorly, diagnose and repair is needed, what would be your approach to this? What would be the logical thing? How would you go after this? What's your plan?
Well, does it have like clear flood mode? Can you try and see if there's a mechanical issue first? Or no?
It started and ran just then. So.
But to see if there was a dead hole?
Oh, he's saying relative compression.
Yeah, like a relative compression.
See if we had a mechanical problem.
Okay. I don't have that on this simulator, no.
All right. If that's good and I don't have a code.
Let's say it's good.
Yeah. All right. If that's good and I don't have a code, I might unplug something just to see which one doesn't react. Just so I get a baseline, like if it's one cylinder.
Let me ask you a question. If the work order says the check engine light comes on and it runs poorly, wouldn't you go after a code? Just to see if it was one?
It said don't use the scan tool.
Oh, I broke those rules. I said, that's all right.
Oh.
We're going to use everything we've got here because they gave us one.
Yeah, this is
Okay.
real.
Well, yeah. Then
This
I would check the code.
this is real world. Okay, yeah. I don't want to cramp your style. It's real world here. So
Yeah.
I'm going to turn the key to the turning a key with a mouse is a little harder. I'm going to turn the key on. I'm going to identify the vehicle here. And oh, look, it's not going to let me pull codes. Okay. Your scan tool is not up to date, Paul. We can't communicate with with this vehicle. Back up and punt. What do you want to try now?
I'd try and see if I can find out which cylinder it is. Either that or if there was a common, like a fuse that controlled everything, I might hook an amp clamp up to it.
Okay.
Like
So I'm going to
for
put
injectors or coils or something like that.
Okay.
Try and do the simple stuff first. See if you could pinpoint what cylinder it is.
Oops. I drug the car instead of the corner of the wiring diagram. I'm strong. I didn't know I could move the car that easy. All right. So here's your wiring diagram. You've seen this before.
Yeah.
It looks like what? Here's our fuse and our relay that controls our 4 injectors, our EGR valve, our canister purge solenoid, and our throttle control module all get power from this fuse. When I had the thing started and running, did it sound like it was a pretty steady miss to you?
I couldn't tell with the phone speaker I got.
That help at all?
I don't know. It just sounds like white noise to me. I'm sorry.
Okay. Do you see the engine shaking?
No.
He's on his phone. It might be tough.
Oh no. Okay. So you're really in tight here. Hard to do.
Is it shaking?
It
Yeah,
is
it's
shaking
a little bit, and it sounds like it's got a bit of a miss. Yeah,
All
like
right.
Jack says, I hear a skip. I agree.
Then yeah, I would try and pinpoint which cylinder the easiest way I could.
Not letting you.
Well, wait a minute.
That's weird. Can we? That's only 15%.
Yeah, it's not giving me the ability to cancel an injector. Bummer.
Can you just unplug the injector?
We can. I know some guys will have heartburn with that, but let's do that. Anthony jumped in to give you a hand here, if you don't mind. So, pick an injector, Anthony.
I'd start with 1.
Oh, okay.
Number 1.
Did
Sounds
I just win?
Play the lotto.
You just we don't know why yet.
No.
Let's unplug 2. Ooh, that got worse. That got worse. I did 2 and 3 and 4. Okay. So all we know is that the cylinder that's not contributing very well right now is cylinder number 1. So now what? Well, let's make our new plan. Our scan tool's useless. Somebody ran over it. What other tools do we have available to us, and how can we approach this? Could it be ignition?
Could be.
I mean, for all we know, since we don't have a scan tool, this could be an ignition problem that's been detected. We have a check engine light on, but we can't get a code. This could be an ignition problem that's been detected, and it's turned off injector number 1. Would you guys
Yep.
agree with that?
Yeah.
So how would we figure out if injector 1 or the ignition is even working?
Voltage. Check voltage to see if it's getting power and ground.
Just swap it.
Brian, we can swap it,
I'm kidding.
but I hear you. I hear you. Swapping a fuel injector, I got a heartache with because of all the O-rings and all that disturbance and everything here. But we can do it. We got one of these things, which Paul, if you're on a phone, I've got an oscilloscope up here.
I can see.
So I just hooked the oscilloscope up to ground. What do you think? Should we look at maybe the injector control?
Yeah.
Okay. So what wire would you hook up to? Turn
The
those
non-red
down.
one.
The non-red one. I like it because red comes off the fuse. Those are the powers to all of them. How many of you guys like to test a known good first?
Sure.
I do. Known good. All right. So I'm going to go to 2. Up. Oh my goodness. My mousing skills tonight are, there we go. And can you see that pattern, guys?
Yep.
Okay, so if I'm at 20 volts a division, that looks like vehicle power. That looks pretty good. It's saying I've got 13 volts. And it looks like I'm pulling this one to ground pretty well, yes?
Mm-hmm.
And what is this thing here?
The inductive kick.
The inductive kick. And what do we know? Where does that inductive kick come from?
Collapsing magnetic field.
So we turned on that injector, we built a magnetic field, and when we turned it off and the magnetic field collapses across that injector, that's a magnetic field moving quickly across that wire, and that produces that voltage. So that's what we know. And we're getting, what, 60 volts off of that? Would you agree with that? It's
Yeah,
20
probably.
volts a division, 20, 40, 60.
Yeah.
All
That's
right.
about right.
Let's go look at our other one.
All right, so you got no inductive kick.
Okay. So now the question becomes, what is wrong?
Probably a weak magnetic field, open coil windings inside the injector.
Can it be an open coil winding
Oh,
with the voltage pattern that we have?
no, because it's getting battery power, so it would be a weak, high resistance.
Okay. I want bets on the side. How many people think that that injector has high resistance versus low resistance?
Put in chat, low or high.
Oh, you got one vote for high. Just coil to coil short. So Sean, you're saying that in the windings, if I was supposed to have 200 windings, I'm just going to make up a story. Winding 37 touched winding 98, and we lost some of our conductor, which means, yeah, okay. So Sean and I are in agreement in what he's thinking. So I'm getting some highs. Sean, yours would produce a low resistance, wouldn't it? Because we've shortened the wire, so there's going to be less resistance, right? Yeah, okay. So let's try and figure that out. Let's shut this off. We don't have an amp clamp, unfortunately, but we do have multimeter. Oh, I'm going to have a conversation with who wrote this one. Could be.
Hey, Jim, let me chime in here for a second.
Yeah.
I'm looking at the answers here, and we have coil-to-coil short, we have high resistance, and I'm thinking back to those laws that Rich hates so much. And when we talk about building a magnetic field, what were those factors again? Oh, the amount of current. So the amount of current is determined by voltage, which we've got, right?
Yeah.
And it's determined by the resistance of the inductor. And this looks like we've got high resistance. So in that case, Anthony's right. But wait a minute, there's something else. Another factor is the number of turns in that inductor. And if we have a coil-to-coil short, we effectively have fewer turns. So Sean's right.
Randy, you're not supposed to pull back the curtain. Remember, pay no attention to the man behind the curtain. The conversation was designed to, I wanted to take a bet, so I took a bet, and I wanted to get everybody else to chime in on the bet because it got everybody thinking. And so if you gave your answer for the right reason, as Randy just jumped in and let the cat out of the bag, fantastic, because that's exactly the type of logic we were looking for. So, and Robert, I love that answer. He says, which is why I had no idea. So he was choosing to be quiet because who knows? And we won't know until we actually do some testing. So if we had a current clamp on this, we had a good circuit here because we were pulling to ground, but we weren't getting any current flow, so we weren't getting a good magnetic field. If we had a shorted coil, like, who was it? Sean, if we had a shorted coil like you and I were putting our money on because we wanted to be the odd person out, we would have seen high current flow. But because we were doing high current flow through less windings, we wouldn't get much of an inductive kick there either. And we weren't getting a strong enough magnetic field to open the pintle there either. So the question could be either. And so, Brian, yes, we could swap these, but instead we're going to go ahead and pull this one out. Oops. And then we'll select to replace with a known good. And we'll put a known good one in, connect things back up, start the car. And we go back with the same test we did. We've got a good pattern there. And we now have a good pattern at injector 1. And we have most likely diagnosed the car appropriately based on the tools and the techniques and the information we had. Everybody good with that?
Hey, Jim.
Yeah, what?
Can I jump in here for 1 second?
Yeah, just don't hurt yourself.
I'll be real quick. Bring the wiring diagram back up. please.
Okay.
So a couple of people said amp clamps. They would use your amp clamp. Fuse F5 or fuse F2. If we were to pull those fuses out, put a loop of wire, put an amp loop in there, and put our amp clamp on it, we could see all of the injectors or all of the coils, depending on which fuse we were on. And it was a question that came up Monday. Let me see if I can share a screen here for 1 second. Oh, where did my... So kind of funny, this waveform was provided to me by Paul Smith, who we just had on there.
Awesome.
This is a 2009 Ford Escape, and he has his amp clamp on the fuse for the injectors. So I'm going to zoom in here a little bit. It's a 6-cylinder engine, and you see current ramp, current ramp, current ramp, current ramp, and then a blank spot. We have a dead injector. And if I zoom in a little bit more, we start to see current ramps. We also see significantly different peaks in current. And if we go to those laws that I love so much, using our amp clamp, we see the current being used by the injectors as they are operating, and using our Ohm's law, we can calculate the resistance. But I'm going to zoom in even more here for a second, because the question that we had Monday night was, if we did this, could we see the pintle hump? And yes, if you zoom in enough, and you can see I'm significantly zoomed in because there was a lot of time on the screen, we can see the pintle hump of, whoops, I moved that too much, of every single current ramp that we have. Sorry, I got too much on my screen here. So
Okay.
this is the reason that Paul and Brian and a couple other people said go to the amp clamp, because it's a quick, non-intrusive way to find out. If we did that on that car, we would see that.
Can I ask a question since you have this up?
Sure.
Is there another channel that you or not have open right now?
Oh, I think somebody's familiar.
Paul, are you chuckling? Was that you chuckling?
Well, it's my waveform. So.
Nice. All right, just
let me get it.
Randy, I'm going to ask
There we
I'm going to ask for forgiveness later. We're going to do a quick teaser on something that's coming in the not too distant future. Zoom in and put these.
I'm going there. Let me get.
So actually, yeah, that section right there. And Paul, without giving away the farm, is there a little bit of an art to this technique? You got to kind of get used to using it. And
yeah, definitely. I'm no expert at it, but Rich helped me figure it out.
Okay. So
I just thought that was a beautiful pattern.
This was awesome, and we're going to share more about this later. But here's an interesting thing that I see. I don't even have to know exactly what's going on, but I can tell you that what you're looking at here, and we're going to do an entire lead-in class on this because Rich and I have been playing with this for over a year. These are your current ramps from your injectors and a missing event because we have either a bad driver or a bad injector. I don't know what the diagnosis was yet. Looked like it was an open injector, probably. What the red traces are is an ultrasonic microphone probably touching the fuel rail.
Yeah.
Okay. And you can see the difference in the intensity of sound from each injector. And I'm going to say that the one there at the 87.46 time base, if you see it has a lower current flow, which means it probably didn't build as strong a magnetic field. It also didn't make as much noise as the other injectors. And the one that's missing basically was a whimper or nothing or just ancillary noise. So there's lots of different ways to come at things, and we're going to talk about that one later. Put it away. We're not going to get distracted by that. Randy, I know we're getting late here, and if people have questions, we're gonna definitely go after any questions that people have. But you had a really slick slide stack on doing something exactly like Paul just described with transmission control solenoids.
Oh yeah, we can
Do
go
you
into
still-
that. No problem.
You want to close out with that one, and then we'll see if there's any questions. And hopefully we've started to delve into the topic of magnetism and mechanical control and diagnostic strategies using that type of stuff. So,
And while Randy's bringing this up, Robert brings up a really good point. Can't you also see the pintle closing on the voltage screen? Yes, because again, piece of metal moving, closing, disrupts that magnetic field, and in the inductive kick, you can see the pintle closing.
awesome.
Okay, I have to apologize. My Zoom crashed there for just a minute. So anyway, here we are. Just a quick show of hands. How many guys out there are trainee guys?
Transmission?
Yeah.
Repair? Okay.
Transmission repairman. Yes, thank
No
you.
comment.
Okay, we got one or two. Early in my career, I was given the opportunity to become the shop transmission guy. That was about the same time the 700R4 came out. I hated that. So,
Good money.
yeah. So I hate transmission fluid running into my armpit. That's all I'm going to say about that. This is a solenoid test on a 5R55S. And we're going to take a look at what the OE says. And the OE says, well, you need to take some resistance measurements. And we're going to check pin 3, which is solenoid power, against all the rest of them. So we're going to check 5, 6, 14, 15, and 16. We're checking 5 different solenoids. And that connector, if you're not familiar with it, points up, I believe. So you need a mirror and 2 extra joints in your hand to look at it. Kind of a pain, to say the least. So I'm going to suggest something a little different. I'm going to suggest that we take a current clamp, and since that solenoid power is shared by all of the solenoids, we're going to put our current clamp around there so we've got a single hookup, and then we're going to exercise these things via a scan tool. So let me show you the first slide. Okay. The first slide is pin 3 and 16, that shift solenoid A. And we also have a picture of a bench test there of the actual resistance measurement. So if we take a look at this, let me get a little laser pointer going here. Okay, if we take a look at this, we have 0 amps right here. And when we turn it on, we build to, well, about a half an amp. So if we take 12 volts and a half an amp, that should equate to about 24 ohms. So we're close, right? So there's Ohm's law in action. Also, we can see the condition of the inductor. Inductors should be really predictable. One of the things that really stands out to me, always has, with Faraday's law, is Faraday's law says that if you have a good inductor, no matter what that inductor is, it should resist a rise in current when we apply voltage and ground to the circuit. Did we resist a rise in current in this case?
Absolutely.
Absolutely we did, because we did not go straight up. So we know we have a good inductor. We know the resistance is about right because of our peak current. And we need to know one other thing, and that is this. This is that pintle hump. Now, there was a little bit of confusion as to why that pintle hump happened in Monday's class. So I want to clarify exactly why that little deviation happens. It happens because we had metallic mass within that coil move, and when it moved, it disturbed the magnetic field, and it caused those lines of flux to deviate, and therefore causes our current rise to change. And that's exactly what a pintle hump is, and that's what causes it. So that being said, everybody good that shifts solenoid A electrically and mechanically is good. I'm not going to comment on hydraulically yet. Okay.
I'm good.
Looks good.
Okay. Well, let's take a look at, let me switch here quick. There's solenoid B, same thing. Everybody good with that?
Looks good.
Resistance is about right, correlates with the current that we're measuring. There's shift solenoid C, about the same thing. Everybody's happy, right?
Mm-hmm.
Okay. Here's solenoid D. And finally, here's the 1-2 shift solenoid. Well, the resistance test measures about 19 ohms, which is not far off of spec. Solenoid current that's measured is 0.725. Okay, so we're pretty close. Not perfect, but it's pretty close. But what's really wrong here?
No hump.
No hump.
No
Nothing
mechanical
moved.
movement.
No mechanical movement. Nothing moved. So think about this for a minute. We would have done a resistance test on this solenoid bank and everybody would be stellar except one, and it's pretty close. Okay. What we did not know, or what we could not know doing a resistance test, is whether or not that solenoid actually moved. And forget about hearing it click inside the transmission. That ain't happening on this one. So anyway, if we really truly understand the characteristics of an inductor and how it should react to the application of voltage to that circuit, and how current should rise, and how the magnetic field can deviate and make that current rise change, we can start to really understand what that picture is telling us. Now, I'm sure a lot of you guys out there have done this kind of thing and tried to recognize pintle humps for years. But keep in mind, this is not just for injectors. This is not just for shift solenoids. This is for anything that has any kind of a metallic core and will move within that device, and gives us a wealth of information. One hookup, a few button pushes on the scan tool, and you're done. And my favorite part, no transmission fluid down your armpit. So yay. Yeah.
Awesome. Well, we've gone well past the hour and a half of presenting material. So I'll apologize in advance for that. But we did allow time for any questions or any input on what you guys would like to see next. Show of hands, how many were intrigued by that waveform that Paul shared that we brought a secondary capture into? Put your hand up and leave them up there if you're interested in seeing more of that stuff.
Nice.
Okay, so yeah, I think we'll make that happen before too much time goes by. There's a bunch of material we already have collected on that, and I would love for everybody that's in the room, keep your eyes peeled for that one, and when we put it out, share it with your friends. And here's Rich and mine's goal with the project that we've been working on is we got kind of excited about it and we got a little carried away with it and we took it in some crazy directions and we learned some things, and we want to share it with you guys and have you all add to what we learned.
Take it to the next level.
And take it to the next level, because you guys take what we can tell you about it and apply it as you see fit and figure out what all we can do and what all we can't do. And that's how we all get better. So we're really excited about bringing that topic to you. And Paul, you already have jumped in and played that game. So even though I haven't met you in person yet, I don't believe, awesome. And thank you. So that's very cool. So any questions or comments or suggestions about electrical topics? I know Pete's gonna, Pete's in the audience, isn't he?
Yes, he is.
He is.
Pete's gonna be involved in the near future with another one. So
Say, Jim, we got to address a really good question by Danny. And he is saying, or he's asking, can you only see the opening on amperage current ramps and closing on voltage? And that is absolutely correct, Danny.
So I have a pop quiz. Show of hands again. How many of you guys have seen a scope jockey class where they're measuring the amount of time it takes to turn off an ignition coil. How many of you guys have ever seen that in a class?
Ooh, ooh.
Okay. You guys don't count. I'm asking the audience for a show of hands. They raised their hands. Have you guys ever seen that? Really? Got one? Only one?
No, we got 3 or
Okay. I must have missed them.
Uh,
They must have.
we had a couple.
We had a few. Okay.
Yep.
who
I'm
wants
sorry.
to stay and play?
No. So here's the question. Based on everything that you've learned tonight, Anthony, you've already got your mic on. Brian's got his mic on. Based on these laws and rules, why is the turnoff time of an ignition coil driver, why is that of interest to me? And why would I bother measuring it with a scope? What am I really looking for? Brian, your mic's up. Paul, your mic's up. Anthony, your mic's up. Randy and Rich don't count. They know what I'm looking for. Paul, you unmuted yourself. What would be your comment on that?
Well, the faster you close that magnetic field, the more voltage you get. If you close it real slow, it doesn't have the same effect. You don't get the spark line that you want.
And we're talking like really short time periods, aren't we?
Yeah, I forgot what the spec was. I got it written down, but I don't remember what it is. It is very small.
I don't try and remember it, Paul. I'll be honest with you. I don't try and remember it. If I have a coil on plug system and I'm suspecting, if I have an ignition coil that's misfiring, the ignition coil could be perfectly fine, and it could be the driver in the computer can't turn off fast enough. Would you agree with that statement?
Yeah.
Yep.
So instead of memorizing the spec, I'll look at the one that's misbehaving and the one that's not. And if the one that's misbehaving is turning off really slow in comparison to the others, I pretty much have an idea what's going on, don't I?
Yeah.
So those are the kind. Go ahead, Rich.
I was going to say the kind of rule of thumb is less than 50 microseconds. So it is super, super fast.
It's not half fast. It's real fast. There you go.
I have that queued up if you want to see it.
I can't say I've ever seen that before. That's interesting.
Go ahead and cue it, Randy. It looks like
Let
we
me-
spurred a little bit of conversation there.
Let me show that to you.
Probably
All I have to do is find it.
And it was not quite. Was it teed or cued?
Queued.
Cued. Okay. By the way, I
Okay.
really appreciate guys coming in and chatting tonight.
Yeah, that was awesome. Okay, here's a little overtime for you here, guys. This is a Dodge coil-on plug system. It's a 2-wire coil, so it's controlled by the PCM. And so we have our current ramp here, and we have our voltage here. So we've turned this on. You can see the voltage pull low. We start to build the ramp. So far, does this follow Faraday's law? Has it resisted a rising current?
Yep.
Yeah, absolutely it has. Now, there's 2 types of ignition control as far as limiting current, because you do have to limit current somehow. You can limit current internally within the module, like the old GM systems, and in that case, you'll see a little flat top across the top. This coil-on plug system, as most are, is controlled by the amount of dwell. And Chrysler, in fact, uses an adaptive dwell system. They can monitor how much dwell it took to produce that spark and produce that duration. So anyway, that's that. Let me go ahead and zoom in on this. And we're going to take a little closer look at our inductor. Now, this is a known good. And so I'll just zoom in on that quick. There it is. Now we better zoom in on it a little more, because we're measuring down to microseconds. Okay, So let's bring a couple cursors out here. This is where we turn that driver off, and this is where the current actually stopped flowing. This little oscillation here is known as ringing. Any good inductor that isn't suppressed with some kind of a capacitance in the system should show ringing when, I'll borrow from John Thornton, when it changes from something to nothing or nothing to something. So.
And as a just a bonus side note, Randy, on some systems with the right tool, you can see the ringing.
Yep.
Or you can hear the ringing.
Like what was that again?
Yeah, never mind. Yeah, we'll get to that later.
We'll get back to that. Okay, I know this is hard to see, so I'll read it out to you. That turn-off time is 3.853 microseconds. Microseconds, not very much. And so that's where the speed of our induction rules comes in. How fast are we collapsing that magnetic field? If you have a damaged driver, for example, and it's not turning off cleanly, it's leaking a little current through, it didn't shut off right away, you could put 100 coils on that thing. It isn't going to make any difference because the problem is in the driver. And to my knowledge, this is the only way to really measure that is using a current clamp. And it's very commonly overlooked if people are aware at all. But, you know, if you've got that one where, well, I put this coil on it and I put that brand on it, and maybe we ought to go OE. Oh, my favorite. Must have been a bad batch. Start looking at things like turn-off time on the current side. So,
if you guys get a Ford, like an escape in, there's a TSB for, you know, if you have a failed coil, replace all coils, all plugs, and the PCM. Well, before you go doing all of that as a proper repair, grab your scope and take a look. You'll see just how bad those drivers can be damaged. Even cylinders that are probably firing fine.
So
do we want to answer Ezra's question there before we sign off?
Oh, let's see. Can a stethoscope rod with a first look delta pressure sensor possibly produce the same or similar ultrasonic waveform? I saw something similar by Trained by Techs.
I can actually answer that one.
Can you?
Because I've done it. The ultrasonic microphone is much more sensitive. There are, and we have a Trained by Techs video where we use the stethoscope rod and the first look style sensor. Hans Jorgensen does it to pick up some noises on a belt or accessory drive, and it works great for that. But it's not accurate enough or sensitive enough for picking everything up. That's something we'll address in future classes there. It's a good idea. It's cool. It works great. But using the first look sensor, it just isn't as sensitive as that ultrasonic microphone.
Yeah.
So,
and it is not a stethoscope.
True. Yeah.
Not a stethoscope.
Yep.
That's for future class.
Can you tell this topic is dear to Jim's heart? So he's busting at the gate to show you guys. So we'll do that.
All right, Randy, you got to remember, I've been playing with that stuff since the turn of the century. That was 1999 to 2000. I got the first unit.
All right. That being said, everybody stay safe out there. Good night, all.